Hello all. So today we will talk about exercise 3.32, Atwood 6. So this is asking us to find the accelerations of the two masses. So first let's call the left mass mass 1 and the right mass mass 2. But just keep in mind these two masses are equal. I'm just giving it a number here so it's easier to list out the equations later on. So first let's observe the system. What do we know about the system? So we have three pulleys, and there's a continuous piece of string going here, around it, and going around this one, going up, going around it, and going down. And the mass is connected here, and there's another mass here. So what do we know about this system? Well, we know that this string, it is massless, and it is continuous. So there's only one single piece of string. And so this implies that tension is constant. Because if tension isn't constant along this string, then it will result in an infinite acceleration of one of these massless segments, which is impossible. And so that's why tension is always constant along the string. So next, what can we do? Let's try to list out the F equals to ma equation for each mass. So remember we said that this is mass 1 and this is mass 2. So for mass 1, we have m times acceleration of the first mass, ma1, equals to just a tension pointing up and a gravity pointing down. And so it's t minus mg. And for this mass, it's ma2 equals to, so for this one, there's tension and there's gravity here. This tension comes from this and that. So it's 2t minus mg. And next, what can we do? Let's try to maybe work with length conservation. So we know that for this string, because it is incompressible, we know that the change in the length of the string is always 0. And what is that equal to? Let's say mass 2 changes by height, delta y2. What is the effect of this delta y2 on the total length of the string? So let's observe. So you have a pulley here and two pieces of string connected here, and the mass 2 over here. So imagine if this mass goes down by delta y2. What happens to these two strings? Well, wouldn't this string go down by delta y2, so this side, and so is that side, go down by delta y2. So delta y2 will result in a 2 delta y2 to the string length. And then this length, the height of this mass will change, which is delta y1. And the effect is also just delta y1. And the height of this pulley will change too. Let's call it y pulley. And so it's delta yp. And that is always equals to 0 because the string is incompressible. But from here, we don't really have anywhere to go, right? Because we have three unknowns. Like, you can do 2a2 plus a1 plus ap equals to 0. But that isn't the optimal way to do this because we have three unknowns. So there isn't really any way to find any relation between a1 and a2. So let's go down another path. What do we know about these pulleys? Well, these pulleys are massless. So what does that imply? Well, that implies the net force of on these pulleys are always 0. Because otherwise, for this equation, a equals to f over m, so m is 0. And then if there's a finite force, there's a net force on it, then this acceleration would be infinite, which is impossible and wrong. So let's say, look at this pulley here. So the second pulley, this pulley here. What do we know about this pulley? So just to draw the setup again, you have a mass here, you have a mass here to the ceiling. And let's look at this pulley here. There's two tensions pulling it downwards and a tension pulling it upwards. We know that net force is always 0, and net force is equal to t minus 2t. And so then t equals to 2t. How is that possible? That is possible only when t equals to 0. In other words, when there's no tension along the string. And so then if we plug that back into the equation here, we get ma1 equals to negative mg, and ma2 equals to negative mg. Cancel m out. We have a1 equals to a2 equals to negative g. And so these two masses are essentially in free fall. So they're just falling down under gravity. And that is our answer to exercise 3.32, and that is quite a strange answer. Thank you for watching.